We are going to see algorithms for finding shortest path in graphs with negative weight edges. Let's see what's wrong with applying the Dijkstra algorithm to graphs with negative weight edges. Consider the node U to be the node which has just made known in the Dijkstra algorithm, meaning that its d of u is freeze. Note that d of u at this point is only based on the paths going through the nodes in the cloud. However, in future we might need to change d of u because of negative weight edges. For example, imagine there's a negative weight edge from a node x outside the cloud to u. The path from the source S to X and then to U might be cheaper than the one from S to U via the nodes only in the cloud. So the algorithm shouldn't freeze d of U at this point and need to allow it to be changed in future. And when relaxing outgoing edges, it shouldn't care whether the adjacent nodes are in the cloud or not. In other words, the notion of cloud shouldn't exist. Here is the resulting algorithm. It is very similar to the Dijkstra algorithm, but with an important difference. The notion of cloud doesn't exist. In other words, the algorithm forgets about the known vertices. The algorithm has an initialization step in which the dist field is set to infinity for all nodes except the source, and the dist of the source is set to 0, and the source is placed in the queue. The while loop starting from the line 5 is the main part of the algorithm. While the queue is not empty, a node U is dequeued and all of its outgoing edges are relaxed. If the dist for an adjacent node V is changed as a result of the relaxation step, it is placed in the queue if it is not already there. Look at the if statement in the line 11 and 12. Importantly, if the dist of the adjacent node doesn't change, we don't put it in the queue unless it is already there. It can be shown that overall, the number of relaxation operations, meaning the body of the for loop from the line A to the line 12, is executed at most O of E times V. The reason for that is because an edge can be relaxed at most V times, and we will see the proof of this in the Bellman-Ford algorithm later. Indeed, this algorithm that we have seen in this slide is a clever implementation of the original Bellman-Ford algorithm that we'll see later. Note that this algorithm can loop infinitely if the graph has negative weight cycles, but we might not know beforehand whether a given graph has negative cycles or not. Later, we will see the actual original Bellman-Ford algorithm, which can indeed detect whether a graph has negative weight cycles. So let's apply this algorithm to an example graph. Consider this example graph with the nodes A, B, C, D, E, where the node A is the source. The algorithm sets the dist field for the source node to be 0 and for all other nodes to be infinity, and also places the source node in the queue. In each round of the algorithm, a node from the queue is dequeued, in this case A, and all of its outgoing edges are relaxed. In this case, the edges from A to B and A to C make the dist field for B and C change from infinity to 5 and 10 respectively. So the nodes B and C are going to be entered in the queue because their dist field has changed, and in the next round one of them is dequeued, in this case B, and its outgoing edges are relaxed. So the outgoing edges are from B to D, and as a result the dist field for D is changed from plus infinity to 8. Therefore, D is also placed in the queue. Now the queue consists of C and D. And the next round, the node C is dequeued and its outgoing edges are relaxed. The only outgoing edge is from C to E, which basically makes the dist field of E to change from plus infinity to 11. So E is also placed in the queue. In the next round of the algorithm, the node D is dequeued from the queue, and its outgoing edge is relaxed. Interestingly, when we relax the outgoing edge from D to E, the suggested value becomes 8 plus 6, which is 14, which is worse than the old value 11. So the old value is not changed. In the next round, the only node in the queue is E. So outgoing edges from E are going to be relaxed. In this case, the only outgoing edge is from E to B with the weight minus 7. The suggested value for B through this edge is 11 minus 7, which is 4, and it is better than the old value, which is 5. So this field for B is changed from 5 to 4, and the node B is placed in the queue for the second time. In the next round, the only node in the queue is B, and we select B and relax its outgoing edges. It makes the node D to change its value from 8 to 7. Hence, the node D is placed in the queue, and in the next round, D is dequeued and the algorithm continues. Now, let's look at the Bellman-Ford algorithm, which handles general graphs, meaning those graphs which might have negative weight cycles. The main idea of the Bellman-Ford algorithm is to relax every edge in the graph v minus 1 times, where v is the number of vertices. Let's look at the Bellman-Ford algorithm. It has an initialization step in lines 1 to 3, where for all the vertices the dist field is set to infinity except the source, for which the dist field is set to 0. The main part of the algorithm is lines 4 to 8, where for v minus 1 times in line 4, we relax all of the edges in the graph in lines 5 to 8. After the line 8, the dist values will have the shortest path weights from the source to all the other nodes if the graph doesn't have a negative weight cycle. But how do we know whether the graph has a negative weight cycle or not? We do one more last round of relaxation of all of the edges in lines 9 to 11. If as a result of this last round of the relaxation, the dist field of at least one node is changed, then the graph must have a negative weight cycle. The Bellman-Ford algorithm has a higher running time complexity than the Dijkstra algorithm. The Dijkstra algorithm is O of E log V, whereas Bellman-Ford is O of E times V. Remember that we relax all of the edges v minus 1 times. But unlike the Dijkstra algorithm, the Bellman-Ford can handle general graphs. Let's look at the correctness proof of the Bellman-Ford algorithm. Consider the shortest path from the source node S to another node U, which goes through some intermediate vertices V1, V2 to Vk. In this slide, we denote the dist of a vertex V by d of V. Here is the invariant of the algorithm. If there is no negative weight cycle, then after the ith iteration, d of Vi becomes equal to the cost of the shortest path from S to Vi. Here is the intuition. The dist of the source vertex S is set to 0 initially, which is equal to the shortest path from S to itself. Then after one round of relaxing all of the edges, in particular, we relax the edge from S to V1. Since we assume the path from S to U is the shortest path, all of its subpaths must be shortest path as well, which means the edge from S to V1 is on the shortest path. So by relaxing this edge, d of V1 becomes equal to the shortest path weight. If we relax all of the edges in the second round of the algorithm, the edge V1 to V2 is going to be relaxed. And with a similar argument, the value of d of V2 becomes the cost of the shortest path from S to V2. So after the ith iteration, we can show by induction that d of Vi will be the weight of the shortest path from the source S to Vi. Now let's formalize the intuition as a proof by induction. For the base case, we know the following. D of the source node S is set to 0 by the algorithm initially, and the shortest path from S to itself is also 0, of course if there is no negative weight cycle. Therefore, the base case checks out, since d of S is equal to its shortest path. Now for the induction step, assume that d of Vi is equal to the shortest path from S to Vi, and we want to prove that after one more round of relaxing all edges, d of Vi plus 1 becomes the weight of the shortest path from the source to Vi plus 1. Now, imagine d of Vi, which by the induction assumption equals to the shortest path from S to Vi. After one more round of relaxing all of the edges, the edge Vi to Vi plus 1 is also relaxed in particular. Since this edge is on the shortest path, the value of d Vi plus 1 must become equal to the value of the shortest path from S to Vi plus 1, because d of Vi is in its lowest value, the shortest path value, and Vi to Vi plus 1 is an edge on the shortest path. So going from S to Vi and Vi to Vi plus 1, it gives the shortest path, and by relaxing that edge, we get the weight of that shortest path. and that completes the proof. Now let's apply the Bellman-Ford algorithm onto our running example graph. We have 5 nodes in the graph, so we need to relax all edges for 4 times, plus one more last round to detect the negative weight cycles. The disk values are initialized in the beginning as shown in the first column, so the disk value for the source node A is 0, and for all of the other vertices is set to infinity. Then all of the edges of the graph are relaxed, the order is not important, and after one round of relaxation, we get the numbers in the second column. We do the relaxation one more time, another time, and another time. So at this point, the disk values for the nodes should be equal to the shortest path values from the source if there is no negative weight cycle. So we do one more last round of relaxation of all of the edges to see whether the disk value of any node changes, to detect whether there is any negative weight cycle. Now let's assume that we are given a directed acyclic graph with negative weights. The question is, can we design an algorithm which is more efficient than the Bellman-Ford algorithm to find the shortest paths for DAGs? The answer is yes, and the idea is based on the idea of the Dijkstra algorithm. Remember the Dijkstra algorithm? It maintains a cloud denoted by the set capital A containing vertices for which we have found the shortest path weights. The vertex selection rule in the Dijkstra algorithm is greedy and is to pick the vertex u from the node outside the cloud, v minus a, for which the estimate for the shortest path is the smallest. Now, we can change the vertex selection rule and get an algorithm which provably works for DAGs. Let's fix the order of selecting the vertices based on their topological ordering. Imagine we have picked a vertex u according to its topological order. Note that u doesn't have any incoming edges from vertices in v minus a. Why? Because those nodes outside the cloud will appear after u in the topological order. Hence, they don't have any edge to u. The claim is that d of u is in its smallest value. Why? The reason is there is no way that the d of u changes due to change of d of other nodes in v minus a, because there is no edge from those nodes to u. So possibly if in future d of those nodes changes, it doesn't affect the d of the u. So the current value of u at this stage must be its lowest value, meaning that the shortest path from the source to the node u. Here is the resulting algorithm. Like previous algorithms, there is an initialization step in lines 1 to 3, and in line 4 we find the topological ordering of the nodes, and in line 5 for each node in the topological order we relax all of its outgoing edges in lines 6 to 9. Note that unlike the Bellman-Ford algorithm, there is only one round of relaxing all of the edges, and the order of relaxing the edges is based on the position of the tail node of the edge in the topological order. Let's apply this algorithm onto our running example graph. We first topologically sort the nodes to get the list of topologically ordered nodes A, C, E, B, D, and we initialize the disk values to 0 for the source and infinity for the other vertices. Then we pick a node from the topologically ordered list of nodes and relax all of its outgoing edges. We pick A and relax the edges to B and C. We pick C and relax the edge to E. We pick E and relax the edge to B. We pick B and relax the edge to D. And finally, we pick D. To summarize, we talked about the following algorithms to find the shortest paths. For unweighted graphs, the breadth first search, or BFS, can be used to find the shortest paths with the time complexity O of E plus V. For weighted graphs, if the weights are non-negative, the Dijkstra algorithm can be used with the time complexity O of E log V, where it greedily picks vertices and relaxes all their outgoing edges. For general graphs, though, the Bellman-Ford algorithm can be used with the time complexity O of E times V, where the algorithm relaxes all of the edges in the graph for v minus 1 times. If the underlying graph is a dagdo, we can do just one round of relaxing all of the edges according to the topological ordering of the nodes and find the shortest paths. The time complexity of the algorithm would be of E plus V, which is very, very efficient.